Welcome back to Modeling with Exponential Functions. All right, we have a person invests $4,000 in stocks today. Be nice to have 4,000 bucks, wouldn't it? And the value triples every 15 years. Let V of t be the value. T years after the investment, determine an equation. All right, so V of t would be, we know our A value because we know we started with $4,000. And then it says our investment triples. Well, that tells us our B number is 3. And it's very tempting to just put a T there, but that's not quite correct. And let's see why. This would say when I plugged in 1, I would have 4,000 times 3. This would say my value triples every 1 year. And that's not quite true. It triples every 15. The way we fix that is we take this T and we divide it by 15 for the 15 years. So now what happens is if I plug in 15, I get 15 divided by 15, which is 1. So I get 4,000 times 3, so my value would triple in 15 years. All right, so that's going to be a common thing. We're going to see that in the next problem too, where we know our base. Our base is something that we know, but because it's not every 1 year, it's every so many years, we have to divide by that number. All right, so there's the answer for part B. For part A, I mean. Part B, once we have that, it's quite easy. Its value at 20 years is 4,000 times 3 to the 20 over 15. I grab my calculator. 4,000 times 3 raised to the 20 over 15. And that turns out to be $17,306.99. And that makes sense because it should be more than tripled. 4,000 tripled would be 12,000, so it's reasonable that it's about 17,000. All right, let's take a look at number 2 here. A physician injects a patient with thallium-201 to determine how well blood flows to the patient's heart muscle. Thallium-201 has an effective half-life of 2.3 days. Some is lost to radioactive decay, and some is removed through the digestive and urinary tracts. Let F of t be the percentage of the thallium-201 that remains in the body at t days since injection. Determine an equation of F of t. All right, let's talk about half-life just for a minute before we do that. So I'm going to build a little table here with t and F of t. So at time 0, the doctor injects the thallium into the patient, so the patient has 100% of the thallium. What it says is we have a half-life of 2.3 days. So that means that in 2.3 days, half of the thallium has left the body. In other words, there's only 50% left. And then another 2.3 days, which would be a total of 4.6 days, half of it goes away again, and it continues on. So we see that we have our A number. Our A number is going to be 100, and then our B number is going to be a half, because we're losing 50%. We're losing half of it every time. So we're going to have F of t is 100 times 1/2 to the t, but again, this would say we lose 1/2 every 1 day. We don't lose a half every 1 day, we lose a half every 2.3 days. So similar to the last problem, it really should be t over 2.3. So that when I plug in 2.3 divided by 2.3 is 1, and then we would have, well, half of it, so we would lose a half. All right, question B. What percent remains in the body after 5 days? Well, we know it should be a little bit less than 25%, but we can just figure it out. F of 5 is 100 times a half to the 5 over 2.3. I use my calculator. 100 times a half raised to the 5 divided by 2.3. 22.2% is what I got, rounding to 1 decimal place. Reasonable? A little less than 25%. Part C, determine when only 10% will be in the body. All right. So part C, now they're telling us 10 goes over here, and we have 100 equals, times 1/2 raised to the t over 2.3. Again, we don't have the skills to solve this equation by hand. Not a big deal. I'm going to divide both sides by 100. So 1/10 is 1/2 to the t over 2.3. Now, let's think about what a reasonable answer would be if I were to do one more of these. So if I were to go to 6.9 days, I'd be at half of that, which would be 12.5. So it seems as though it's a little bit more than 6.9 days. So using our calculator, I'm going to type in 1/10, and then I'm going to type in 1/2 raised to the x over 2.3, and I can graph. Oh, you can't really see that very well. Move that up there. Now we don't see the 1/10 graph because it's so close to the axis it really doesn't draw it. So we can't see it, but it's there. So we're going to calculate the intersect. And notice it does ask you, is this the first curve? And it does say it's the 1/10, so yes. Is it the second curve? Yes. Enter. And it tells us it's going to take 7.6 days. So it'll take about 7.6 days for the thallium to be down to 10% of what was originally put in there. All right, our last question in this section. Revenue from e-cigarettes are shown in the table below for various years. Let f of t be the annual revenue in millions of dollars from e-cigarettes since 2000. All right, so the thing is, find an equation. What we should notice is this data is exponential. And the reason I notice it's exponential is I notice that it's almost doubling every time. 20 times 2 would be 40. 40 times 2 would be 80. 80 times 2 would be 160. All right, a little more than double there, but that's okay. And then that's about 200. 200 double would be 400. So my data is doubling every time, which tells me that's an exponential function. So, to save a little time, I went ahead and I typed the data in. Notice it says that t is years since 2000, so this first one is 2008. So I typed in the data. Stat, calculate. We want that one, since we want an exponential equation. Calculate. So it says A is 0.04 and B is 2.12. So our equation is f of t is 0.04 times 2.12 to the t. So that's unusual. We have a very, very small a number. And then we see that the value of e-cigarettes is more than doubling every year. 112% growth, more than doubling. That's pretty good if you're in the e-cigarette business. All right, and then it says predicted revenue from e-cigarettes, ignore the typo there, in 2020. So 2020 would be 20 years after we started. So f at 20 would be 0.04 times 2.12 to the 20. I use my calculator. 0.04 times 2.12 raised to the 20. 1,345,17. So that's $134,517 million. All right, so what does that tell you? What that tells you is that's unrealistic. $135,000 million, that's not believable. So what's happening here, this really is a good example of model breakdown. this data that we have, it looks linear, or I'm sorry, it looks exponential. It can't be exponential for very much longer because there's no way you could get this amount of money in the year 2020. It's just unbelievable. Okay, so again, watch out for that. This is a dangerous thing about exponential functions, is exponential functions grow really fast. So if you're modeling data by an exponential function, you cannot predict very far into the future because it's simply going to grow too fast and the answer will be unreasonable. All right, so this is a challenging section, I think. This is one of the harder ones. Certainly the videos are longer. Take your time, do some work on it. Try to read the problems carefully and pull out all the important numbers. And as always, send me emails when you have questions.